along. So in this lesson, we're going to have a look at topic 2. I'll go through in order, and I've just got a few things to say here and there. This is not meant to show you how to do different bits of the content here. We've done that over the last 2 years. This is just where I think the calculator may or may not be useful to do these sorts of things. So here we go. 2.1 is all about straight lines and that kind of stuff. And the only thing I could think of really that might be worth looking at is perpendicular lines, where you've got this in your formula sheet, m1 times m2 equals -1. That's how we figure out the gradient of a line that is perpendicular to another line, by looking at the negative reciprocal. And to be honest, as I've said to you in class, the way I would do that really is I would just do it in my head, kind of. The only time that might be less useful is if it was a number like 6.2. And you're like, well, how do I do that? Honestly, I would probably just go -1 on my calculator, -1 divided by 6.2, like so, and that would give me minus 0.16, etc. But let's just say you've forgotten that relationship, but you do look at your formula sheet and you see m1 times m2 is equal to -1 on your formula sheet. And you think, okay, well, at least I know what to do, but I can't remember how to do it. Just don't forget your old pal menu, algebra, numerical solve. So you could do this. Let's just say 6.2 is the gradient you're given or whatever, and you need to work out what the perpendicular is. So that's m. So you know that's the formula, m1 times m2 equals -1. So you could use nsolve to do that. And of course, it gives me the same decimal approximation. So that's something you could do. Would I do it in practice? No, but it does reinforce the idea that nsolve is there for you to use. You can also use it. I'll just give you one more example of nsolve where the answer might not be as clear as we would like. So let's just say it was the gradient you're given is -3, and you're trying to work out what m2 is. Then you've got, always got to do it with respect to a variable. Then it'll give you 0.3 recurring, which I'm sure everyone can go, oh, that's a third. But just to remind you that when you do have a decimal answer and you do need a fraction for whatever reason, under menu and number, there is approximate to fraction. So it looks a bit weird, but it sort of says answer is input into approx fraction to that many decimal places, and then it will tell you it's a third. So you can convert. So, 0.3 recurring, 0.6 recurring, but what about 0.1 recurring? What's that? Or 0.1212121212. What's that as a fraction? You can use this to work out the fraction if necessary. That's really all I had for 2.1. A lot of it's just stuff that you need to know, and your calculator might be used because the numbers aren't easy to do in your head, and that's about it. Any questions? Alrighty, let's move to 2.2 then. 2.2. Concept of a function, domain and range. The graphics calculator will not help you with that. You need to understand those key terms, domain and range and function. The concept of a function is a mathematical model, and there's some examples there. The next one is where we might have a little bit of traction, and that is the idea of an inverse function that reverses or undoes the effect of a function. Now, the blue GDCs will work out an inverse function if it's in CAS mode. So in other words, as IB students, you're out of luck. It will not work out. But you can kind of use it. So I'll get the calculator up and I'll give you an idea of a function. Let's use f of x equals x squared plus 1. So I'm going to use my calculator and I'm going to go f1 of x is defined as, remember, control that button there, so colon equals. f1 of x is defined as, and let's just say the function I was given was x squared plus 1. Are you with me so far? Let's say now that the question says, what is f of negative 1, i.e. the inverse function of f? What is f of negative 1 of 5? Now, technically, the function's not that difficult, x squared plus 1. I'd probably just work out the inverse function and then substitute x equals 5. But you could do it like this. If you remember that what makes an inverse function is that the domain and the range swap over, right? So if it's f negative 1 of 5, then I'm basically saying what is x when f of x equals 5. That's what it means. Does that make sense, or do you want me to do it on the whiteboard to explain? Okay, this will be good for the video, won't it? So I'll just say what I'm writing down at the same time. So let's just say you're given the function f of x equals x squared plus 1. So the function has a domain that maps onto a range. We know that, right? We should know that by now. The domain is the set of input values. So remember Dixroy, domain is the set of input values, and the range is the set of output values. Okay, so if we talk about f of 2, what is f of 2? 2 squared is 4 plus 1 is 5. So we would be saying that when I input 2 into f, we replace x with 2, so we've got 2 squared, making 4, and add 1 to it to 5, so the output is 5. Okay, so the domain input, the range is output. Is that okay so far? That's fundamentals. So if you're told what is f of negative 1 of 5, then just based on the working I've done over here, over to the side, I should get 2, right? Because the way it works is effectively the range of f of x becomes the domain of the inverse, and the domain of f becomes the range of the inverse. Okay, so its domain, the inverse's domain, is the range of the original function. The inverse's range is the domain of the original function. I think I might have made a mistake with what I said then. Okay, so I'll say that again to be clear. The domain of the inverse function is the same as the range of the original function. The range of the inverse function is the same as the domain of the original function. They swap places, they swap sets. That's basically the fundamental definition of an inverse. So what does that mean in terms of you've been given a complicated function, not like x squared plus 1 like I've done. You've been given a complicated function and you're asked, what is f inverse of 5? What is that? So if you know what you're doing, you could just use nsolve, which is from menu algebra, or you can type in nsolve. And then because I've defined it up here as f1 of x, what I can do is I can say, well, give me what x is when f1 of x is equal to 5 with respect to x. And it gives me 2. In other words, if I need to find what f inverse of 5 is, then I can solve the original function for 5. And that'll give me what the answer is. I run the risk of making it more complicated the more I talk. So does anyone have any questions that might make that clearer? Otherwise, I'll move on. Hope you're enjoying your drinks. Feel free to hop up anytime and grab some food while it lasts. That's all I wanted to say about inverse functions. That's all I wanted to say about 2.2. So I will move on unless you want to ask any more questions. Okie dokie. 2.3 is all about understanding graphs and sketching, that kind of stuff. One thing I want to point out is that you can be given, have a look at the bit I highlight here. It says that you may be given functions that are not specifically mentioned in this topic. So we know in this topic we cover quadratics. We know that we cover linear. We cover e to the x. We cover log x. We also cover trigonometric functions, but not in topic 2. But there's rational functions as well. We know we cover those, but in the calculator section at least, you may come across functions that are not one of those ones that we've covered in depth, because you're expected to be able to at least understand the concepts of functions and apply them to unfamiliar functions. Okay, so the idea of a domain, the idea of a range, and to be able to graph them as well. So I wanted to point out this bit here, which I think's useful to remember when thinking about the calculator. It says students should be aware of the difference between, sorry about that little thing in the middle, the difference between the command terms draw and sketch. What is the difference? Who can say?
Sketch is like a rough representation and draw is an accurate representation.
Yeah, that's true, but rough might lead you into occasions of sitting and thinking that you can just sort of get away with any old tat on the page. That's not quite true.
Is sketch you don't have to put as much information on it?
That's more the point, Zoe. Yep. It's about the detail, yeah, and which is what you mentioned about drawing, wasn't it? Yeah. So accuracy equals detail, right? So it's not so much rough, although yes, it does take a lot less longer to do, but it's got to do with the information. So with a sketch, you are simply putting down critical information, and it may not be drawn to scale like a drawing might be, but it does contain the critical information. So it depends on the graph, right? What critical information looks like, but just shout out, different people, please. Shout out what could be one piece of critical information on a graph. Y-intercept, someone else? Turning point, yep.
Point of inflection.
Point of inflection, yep. Come on, guys.
X-intercepts.
X-intercepts, otherwise known as? Zeros, yep. What else?
Minimum.
Yep, turning point, minimum turning point, maximum turning point. What?
Intersection.
If there were two graphs, yep, point of intersection. Asymptotes, yep. What else?
Endpoints.
Endpoints if it's got a defined domain, yep. What else?
Area under the curve. Unless it's been said.
It hasn't been said. That's very specific, but it potentially, yes, potentially.
You have to put the arrows.
Don't have to. You should either put arrows at the end of your lines, or this is what I do, or make sure that your graph goes to the your sketch goes to the very end of the axis. Amazingly, because I know you all know this, can you believe it? No one's mentioned y-intercept yet.
I said, yeah, that's my first.
Oh, it's your first thing. Okay. Not amazingly, Richard forgets things that have been said 30 seconds ago. Because, Parav?
Richard's an idiot.
Thank you. We've got that on video now, which is awesome.
Oh, no.
I like how you slurred it too. What did you put in that cup of tea? What else is in there? Most of us. I said most of us.
If I was going to poison anyone, I think I deserve.
Oh, dude, that's hard.
I've used it for 2 years.
Yeah, he just said he wouldn't poison you, Lily.
Yeah.
True. This is all on the video now. It's like...
Anyway,
Guys,
moving right along. Have we missed anything else out? One other thing is that sometimes another critical piece of information is one other point for scale. So if you're doing an exponential graph, for example, there may not be an x-intercept. There will be a y-intercept, but every exponential curve looks the same, right, without scale. So you would put in one other point to show how quickly it's growing and stuff like that. I think that's it. So well done. That was really good group thinking there. Yeah, that too. It mentions here as well that you, I can't think of where this would be really useful. Maybe it's in 2.4. Oh man, where did I see it? Oh yeah, using technology to graph functions, including their sums and differences. So just really briefly, I wanted to point this out because it's useful for other things we do as well. But if you had, say, for example, I'm just going to start a new document up so it doesn't get too confusing. You can define multiple functions. So if I go f1 of x is equal to 2x, and then I go f2 of x becomes equal to 3 cos x, then you can define a third function as the sum or difference of those two other functions, like this. So I'm just imagining that there might be problems where you've got multi-parts to your problem, and I just wanted to get you used to the idea that you can build up your equations like this. Okay, and it's quite handy in that. So if I go f3 of 1 Is it in radians? Yeah. So 3.62, right?
It's not. It's not up. Frozen. It's glitched. Oh, there you go.
It's there now.
Magic.
So you can do F3 of 1 and you get 3.62. And then another part of the problem modifies the first function for some reason. You can imagine they would do that. So now it's 2x plus 1. I can redefine f1 of x, and f3 will now be redefined as well. So, chunking down your problem into mini bits so that you can manipulate bits of it is quite useful using the GDC. Okay, any questions? Please don't hesitate to yell out if there is a question as we go along. Okay, 2.4 then. 2.4 talks about determining key features of graphs and finding points of intersection. So I thought we might spend some time on that because that's where your calculator can be really handy. And remember, you won't always get functions that you know how to do by hand. But in my example, I'm just going to use fairly simple ones just to illustrate what's going on. So I'm just going to add a calculator, and I'm going to add 2 graphs to start with. Actually, you know what? I'll just start with a graph instead. It's probably a little bit easier to start with that. So I'll add a graph page, and I'm going to go, the first graph is going to be just a cubic, which is not formally part of our course, but it could be given to you in a calculator section, plus 3x squared plus 2x plus 1. So that gives us a lovely little cubic like that. Oops, did I? Should be. Nah, I just stuffed up a thing. Hang on. Control G. Use my arrow key, and I meant to make that 3x squared. So x cubed plus 3x squared plus 2x plus 1. There we go. Lovely little cubic like that. And then I might just put in another function as well. So Control G to get the second function up, automatically goes to the first blank spot, and I'll go 3 minus 5x, like so. So there's my 2 graphs. I'm not too sure how much I need to go through with this, so I'll just really quickly do a little bit. So remember, there's a whole bunch of things that you can find under Analyze Graph. 0, minimum, maximum, intersection. They're the main ones for function interrogation. So I can click on 0, and it says which graphs. If you've got more than one graph, you do have to select one of the graphs first. And then you can click either side. And if you want to keep it permanent, single click. And if there was more than one 0, then you could repeat that process for each 0. Okay, so that tells me that one of the zeros is negative 2.32. Analyze graph. Intersection. So I'll go to the left of the intersection that I can see visually and to the right, and that'll show me the point of intersection here. The one thing that I think would be faster to do manually is the y-intercept. You 100% can do it using the calculator, but I reckon, like for a simple polynomial, that polynomial being, say that one there, like substituting 0 in for x and then working out that the y-intercept is 1, surely that's going to be easier than trying to get the graph to trace it. But technically you can. So just as an FYI, if I go to menu and I go to trace and I go to graph trace, looks like it's already selected the blue one. I don't know, it doesn't always go to the y-intercept to start with, but it did this time. And you can see here that as you press the arrow keys, it gives you different values down the bottom right-hand corner. It does tend to lock on zeros. It doesn't tend to lock on maximums and minimums, but sometimes it will. And it will lock onto the y-intercept. So you can get that information through a graph trace if you want to. That's it. I wanted to show you something else, though, that I think I certainly haven't really played around with a lot. And it's not super critical, but you might find times where this is useful. You do have access in the menu button in the algebra section to these 2 solvers, I suppose, equation solvers. So if I go down to polynomial tools and go to find roots of polynomial, it'll say, well, what degree of the polynomial is it? So just to be really clear, a polynomial function is x to the power of something plus x to the power of something plus x to the power of something, and the somethings are always a whole number, whole positive number. Okay, so not square root graphs, not rational graphs. They all, like cubics, quadratics, linear graphs, they are all polynomials. So if I take a degree 3 polynomial, that means my highest term is x cubed. So if I click on OK here, it's now asking for the coefficients, a3 to a0, and you can see a3 is the coefficient of x cubed, and a0 is the constant, and everything else in between. So if I use the same values as I had before, which was x cubed, that's 1, x cubed, and then we had 3x squared, so that's 3. Then we had 2x, so that's 2 here. And then we had plus 1, so there's a 1 there. And click on OK. That's the what the function looks like. And when I press return, it says there is just one solution, and it's negative 2.32. Okay, which was the same as the 0 here, obviously. But there's more decimal places there, which is kind of handy, isn't it? You can use it for multiple solutions as well. So you do need to have it in the format of blah, 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 blah equals 0. But if I go back to algebra and I go to polynomial tools and go to find roots of the equation, this time I'll take a really simple quadratic, and it's going to be x squared, so 1, minus 5x, so that's minus 5, plus 6. So maybe you do it in your head, if you can, really quickly. Wonder what the zeros are going to be. Give you a moment to think about it while I answer Siggy's question.
Or just if you type in like with the letters at the bottom of the calculator polyroots, would that achieve the same thing?
Yep.
So you don't need to like follow the whole thing.
No.
Even though following it would be a lot easier.
Polyroots would be easier, but I definitely would probably type it in for NSolve. Do you know what the hardest thing though is? Because I got no idea why, but they've got the keyboard in alphabetical order, and it slows me down so badly. Anyway,
Well, I almost tried to touch something the other day. It was just giving
not good.
No.
So there it is there, polyroots, and you can see you can just type the equation in there as well. And then we get 2, 3. In other words, one of the solutions is 2, one of the solutions is 3. Yeah? So the factorization would be x minus 2 times by x minus 3. Okay? Just to show you, here's where it might be a little bit useful, Siggy. Polyroots, f1 of x. That's where you might save a bit of time by typing in polyroots, because you can then just type in f1 of x for the equation. Yeah. So that's all I want to say there. Yeah, and one last thing I will do is show you systems of linear equations. Now, the thing is, what I'm about to show you, I still feel like graphing them and finding the point of intersection would be easier. But just proof of purchase here. Menu, algebra, solve system of linear equations. I want to solve 2 equations. That's all we ever need to bother about in Maths SL. Click on OK. You get 2 boxes here. So the first one, I'm going to go y is equal to f2 of x. Do you remember that was my linear equation that I had before? It was 3 minus 5x. So that's one of my equations, which I would type in like that. Why do I not just type in f2 of x? Because have a look at what it's looking for. It's pairs of x and y values. So I say one of my functions is y equals whatever f2 of x is. The second one, maybe I don't have it as a predefined function, so I'll type it in manually, 3x plus 1. So there's my 2 equations. Press return, and there's my point of intersection, 1/4 and 7/4. And as usual, I can go Control Enter, and I'll get the approximate or the decimal equivalent. It's not approximate in this case. So that's a way of working out simultaneous equations without graphing. Any questions about that before I move on? That's all I want to say about 2.4. We've got 20 minutes left, so see how I go getting through the rest of this one. 2.5 is more function properties, specifically around composite functions and the identity function. The identity function is simply understanding that if you take a function and pass into it the inverse function, you should just get the same value out. And I'll show you what I mean in a moment with the GDC. Okay, so what we can't do is it won't work out composite functions for us. Again, as per usual, if it was a CAS calculator, it would, but we don't have access to that. But we can sort of use it a little bit. If we understand that a composite function means that, like, f composite g of x means g of x is the input to f of x. That's basically what it means. Okay, so it's like it passes through. Now, I can't spend a whole lesson talking about what that means. So if you don't get it, that's okay. You'll just have to move on. So I'm going to define two functions. f1 of x is equal to x squared. I'm keeping the function simple so that we can sort of see it. f2 of x is equal to x plus 1. So there are my two functions. Now, again, not good telly, but I'm going to go to the board to sort of explain the composite function idea here. So if I have f composite g, but in this case I've got f1 and f2. So if I have f composite 2 of x, that is equivalent to saying it's f1 where f2 of x is the input to f1. So it's f1 of f2 of x. That's what it means. So if f1 of x is equal to x squared and f2 of x is equal to x, what did I say it was? X plus 1?
Yeah.
X plus 1, then f composed with f1 composed with f2 of x, that's a new function, which I'm going to call, say, f3 of x. If f3 of x is equal to the composite of f1 and f2, what that means is that, well, f1 is the outside function, so I'm squaring, and instead of having x as the input, I have f2 as the input. And what is f2? X plus 1. So the new function is x plus 1 all squared. Okay, that's how composite functions work. So what you could do, so what the GDC will not tell you that. It will not show you at any point it's x plus 1 all squared. But what you can do is you could say, for example, f3 of x is equal to f1 of f2 of x. Okay, so you can put it in composite notation like that, and it will be quite happy with that. So now if it says, what is f1 composite f2 of 3? Well, we know it should be 16, I think. So if I go f3 of 3, it'll tell me it's 16, right? So it will give you numerical results. So unsurprisingly, when we turn off the algebra part of the calculator, which is what CAS is, you're left with numerical analysis only for the most part. So if you're not confident with your capacity to make a composite function work, or that your result's correct, you could always use your GDC to sort of like remove any errors you might make yourself, and it will give you the right numbers. So remember,
If you got a different one from the composite function that you wrote, then you did something wrong.
Good, yeah, that's a really good point, Zoe. And you don't always have time to do that in exams, but when you do have time, using your GDC to confirm what should be the case is kind of a bit of a gold mine, right? Because you don't have an answer sheet. So what I've just done on the GDC is the equivalent of that. F1 composite F2 of 3. Now, in the actual exam, they are more likely to use f of x, g of x, h of x. Personally, I translate them all to f1, f2, f3, etc., because they're graphable. You can use h of x, so I can go g of x is equal to f3 of x. Becomes equal to, otherwise it won't work. And that's fine. I can go g of 3 and I get 16 as well. So that's all fine, but I can't graph g of x. I can only graph f1 to f99. So I tend to just get used to changing them to f1s to whatever. Okay, yeah, I just wanted to go through the identity function as well, but before I do that, does anyone have any questions? Okay, I hope this is useful, guys. You can also use it to check inverses, and this is getting a little bit back to what Zoe was saying. So again, a bit of board work, sorry, video. So let's just say you had a function, and the function was f of x is equal to 3x. I want to get it the same as the example I've got written down so I don't confuse myself. 3x plus 1, yeah. So f of x equals 3x plus 1, and you're asked to work out what the inverse is. Could you do it?
Yeah.
Could you do it in your head? Give you 30 seconds, go. Siri. Okay, that was your 30 seconds up. Did you get x minus 1 on 3? Great. Just for those who got lost, that's the function with y instead of f of x. Swaps these for inverse, because remember, domain and range get swapped. Now solve for y. Okay, so that's pretty simple, but it's not necessarily that simple in the exam. Time pressure plus more complex expressions. So you've got your expression, but you want to make sure it's right. What you could do is you could use your calculator to define both functions. So f1 of x is equal to 3x plus 1. And then you could say f2 of x is equal to what you think. So control divided by, and you reckon it's x minus 1 on 3. I forgot the colon. And then the way composite functions work with inverses is that if I get f3 of x and I say that's equal to f1 of f2 of x, so remember what I'm saying here is that I'm inputting the inverse function to the original function. I should always get the same value out. That's, again, part of what it means to be an inverse function. So then I could test it for a few values. Just a test. f3 of 3, yep, is 3. f3 of -7 is -7, great. f3 of pi is pi, great. It looks like it's working well. So I can say that with fair degree of confidence that my inverse is right. Yes, E.
I'm just going to say that screen's frozen. I'm like looking at that screen.
Oh, is it just one of them freezing at the moment?
He just can't be bothered turning his neck to see.
I'll turn my neck. I'll turn my neck. And he's on a bloody
And he's on a swivel chair. Yeah, exactly. Will he's on my chair. Okay. The other thing I just wanted to point out too is that functions that you define here are in the graph page. So if I do add a new page, add a graph, and I'll just put on f3 of x, and that's what you would expect to get. So if you create a function which is the composite of a function and its inverse, you all the time 100% should get a diagonal line just like this. That's basically one of the properties of an inverse function. That's it. That's all I wanted to say on that. Any questions? Going once, going twice. You all done? You all sold? Okay, that's 2.5 done. What have I got? 13 minutes. Woohoo! 2.6. The quadratic function and its graph, intercept, axis of symmetry, the form. Most of this, your calculator will not really help you with. The only thing that might be sort of useful is that you could use polysolve in order to work out the zeros, if that's all you needed. But honestly, I genuinely think that probably the easiest thing to do would be to graph it straight up. The one thing I would suggest that you don't bother trying to emulate on a calculator is this little baby here, the axis of symmetry, right? Because the axis of symmetry requires you to input a relation into your calculator. It can do it, but it's not worth it, the headache. Just to remind you, the axis of symmetry is the x coordinate of the turning point expressed as a relation. More good telly as I do a bit of board work here. So if I draw a parabola up the top here like so, my x-coordinate, let's say my x-coordinate is 3, like so. The axis of symmetry is not 3. The axis of symmetry is just a number. This is the axis of symmetry. Sorry, 3 is just a number. The axis of symmetry is an equation. The equation is always x equals followed by the coordinate of the turning point. So it's x equals 3. So if you're asked to draw the axis of symmetry, you 100% need to draw a vertical line. 100% would make it a dotted line like this, just like you do asymptotes, and 100% you would label it x equals 3. I think some people are not focusing on what I'm doing on the board, nor are they doing their own work, and that disappoints me. Okay, any questions about that? Alrighty, moving on to 2.7, I think. I don't think there was much to tell you about the calculator. Similarly for 2.7, I know I will do a bit. 2.7 takes quadratics and looks at specific properties, factorizing, completing the square, and solving the quadratic formula. Most of these things are just much easier to just, you just need to use your basic calculator knowledge for that. But I will give you a little example.
You have to know about the Babylonian method.
No. Where's it say Babylonian method?
Babylonian method of
Right, all this stuff here is like suggested sort of stuff of ways you can sort of broaden your understanding to say that,
Is that sort of like
surprise, surprise, equation solving is not a Western European concept.
Richard, would
Aren't
that
we all
be-
shocked by that?
Would that be more similar to like IA related stuff?
Potentially, but really, if I was doing the course really well, then I would. No, I do mean it. I would actually be bringing a lot of this sort of stuff, linking it in as I go along, kind of thing. Whereas I just tend to be a bit more spotty with that kind of stuff. But if I was doing it really well, I would actually bring in these sorts of concepts all the way through the course. I'm happy to admit when I don't do things as well. See, I'm not that fragile.
Sorry.
X squared plus. So what I got here is, so if you were given a quadratic equation like x squared plus 3x plus 1 equals 2, for example, there's a couple of ways you could do that. So I'll just write it up on the board. Although I prepared this lesson, what I didn't prepare is that how much board writing. I didn't think about how much board writing I was going to do. So that's a bit of a failure for the video. So if we have x squared plus 3x x squared plus 3x plus 1 is equal to 2. There are two approaches we can use to solve this. One way is to subtract 2 from both sides. Probably this is the way I would do it. So that you've got x squared plus 3x minus 1 equal to 0. And then I would solve that using my graphics display calculator and looking at the zeros, the intercepts. I'm not going to do that, but is that okay if I just leave it at there? The other thing I will do, which I thought might be something that you wouldn't think about, is that instead of doing that, you can create two equations, one for the left-hand side and one for the right-hand side, just as it is there. No mucking about. So I can go f1 of x is equal to x squared plus 3x plus 1. That's my first function. And then I'm going to add a new graph and say my next one is just 2, the right-hand side of the graph. So one function was for the left-hand side, and now this function is for the right-hand side, like so. Now, if I want to work out solutions, instead of looking for the zeros, I look for the points of intersection. So I'll go menu, analyze graph, points of intersection. Start to the left-hand side. And as I've said before, there are two ways of doing the next bit. Just move it along until you get the first one. Write down the value or values, negative 3.3 and 2, obviously. And then don't click, but just keep on moving until the next point of intersection pops up, 0.303. Or you can click and then it saves it. And then you can do it again for the other one.
scenario where this is just like a lot more useful than doing the subtraction method to make it equal to 0, so you can just write it out as one equation? Just because this seems like a lot more effort, but I'm thinking of like maybe like cases where you're dealing with
This second model is more effort.
yes.
Number one, you might not feel confident about what you're doing, so you might want to keep it as pure to the original equation as possible. Number two, obviously, it might be more complex as well. So it might be sine of x plus 3x plus 2. But whichever way you look at it, you can always subtract it doesn't matter what it is, subtract it all onto the left-hand side and deal with one function. But at some point, you might go, well, the trade-off of me having to do all the subtractions and making sure I make no mistakes is not worth it. I might as well just do functions. I might just point out something else you can do too. Sometimes you'll want to use these numbers, or you want to see the decimal places more than what written here. So you can right-click. I think it's Control-click on the numbers, and it brings up this, and you can store the variables in a name. So I could call this one, say, P1, and then right-click on this one and store it as P2. And then when I go Control plus page, add calculator, and I look at my variable list there, you can see there's my P1 and P2. So if I go P1, there it is to all the decimal places, and then you can substitute it into other functions if you need to, or whatever. It's 2. Amazing. Couldn't believe that was going to happen. Okay. So that's kind of handy to do as well, to be able to store stuff in variables so you can use it elsewhere. Any questions? Just conscious of time. I might finish off there because we've only got about 4 minutes left. I'll let you know where I'm going next. I'll do it in a separate video, although it'll be much shorter, and then I'll try and pick a shorter topic for tomorrow's session as well. And then all the rest of the topics I'll do without you guys in front of me. Tomorrow I'll be looking at inequalities. How do you solve those? I think graphically is way better than trying to do it purely algebraically. Also, we'll have a look at the discriminant problem. I'll literally look at this problem here for that equation there. And we'll see how we can use our GDC to work out values of K. And then we'll be looking at 2.8, 9, 10, and 11. And there's actually not too much GDC work to do there, just more like careful of this and careful of that kind of stuff. And that will I'll leave it there for the recording.